All right, this is the print I just did. If you look at this, this is a square chip, I should say, or checkers. So I wanted you to see that. I'm going to see if I can move this forward or back. This may be off the internet. Yeah, see, it's not acting quite right now. All right, now we're going to start one up. As we go through this, I'm going to move the printer, hook it back up, and we'll have it running. You'll actually see a print here a little bit. Okay? So, with that in mind, today's lesson is going to be about materials engineering. We got a couple questions here before we start. Let me show the screen. We go here. Oh, I can see. There we go. Now we can. Okay? Can you see materials engineering, introduction to presentation to young engineers of today? Raise your hand if you can see that. All right, everybody else can see me here and see me. How about, who's this? Ryan. Everyone else can. Okay, Ryan is trying, can't hear me, so I'm going to go ahead. Hopefully I'll get him. All right, now. Ryan, can you hear me? Raise your hand. That's weird. All right, Ryan. I'll type it here, Ryan. Everyone else can hear me. All right, now, here's what we're going to do. We're going to talk about materials engineering, and we're going to be watching some videos, so we'll copy the video over on a link, so that way if you don't want to watch it on my computer, it's too much lag, you can do it. The first one I'm going to send to all of you is called, watch this link, I'm going to watch it here, it's Modern Marvel's Liquid Metal. It's twice as strong as titanium. It's very resistant to scratches. And the marks, I've got scratches twice here. Marks, to scratches and dents, I should say. This one's being produced, which is usually a really pretty good sign. A lot of times we invent things that are not set. So here we're going to go ahead. I put that link on for you. Let's go ahead and watch this. If you want to watch it on your computer, go ahead. Sometimes people see it better. So we're going to try it up there. Hopefully Ryan can hear this.
I'm Mike Fowler.
Oh, I haven't paused this.
Heating.
As you just saw, they're basically using metals in the glass, making these incredible liquid metal. Another cool one that's out is called Graphene. This was literally, students anywhere could have saved this. All right. Anybody could have saved this. Well, I don't know what to tell you, Ryan. Let me answer Ryan here, folks. Okay. All right, let me do this. I'm going to put up the video link so we can watch it. All right, now, graphene is the strongest material ever measured. It's 100 times stronger than steel. It's the stiffest and it's thinnest. It's an amazing product. The hard part is manufacturing it. And what's wild is it was discovered when these guys literally were taking tape and peeling off graphene, so it got layer and lower and lower and lower and lower and lower layer. It's the most amazing thing. All right? So you could have done this experiment looking at your pencil. All right? So let's go ahead. I'm going to put this over for you. I'll put this on everybody here. If you want to watch it that way, or you can just watch it on my computer. Here we go. Go ahead and pause this. One thing to discover and invent something, another thing altogether to manufacture it. All right? That's one thing I want you to get out of this, that you can come up with an idea. All right? Then, you know, the more innovative, the more breaking the mold the innovation is, the less likely we are to figure out what it's really going to be used for. So in other words, if you really have some great innovation, we may not even know what the product is. Remember, when they made the light bulb, people said, well, you only need one light bulb in a house. They thought of the sun. All right? Okay? So here we're going to try. Give me 1 second here as I try to help Ryan one more time here. All right, now, the more, again, what the point of this is when you get a really fundamental something new, we're not even sure what to do with it. All right? So, and restricting adaptation in the marketplace, or why I don't see this wonderful stuff in the stores, you have to be able to make it, manufacture it, and then it has to be really a lot better and a lot cheaper than existing products. Okay? So let me give you an example. Silicon was discovered about 100, you know, to make silicon was 100 years before we had the silicon chips. Aluminum was discovered in 1850. Chemists painstakingly came out with a way that you could remove a little bit. And it was amazing because they were saying, wow, we're getting silver out of clay. In the 1880s, we were able to mass produce it, where we were able to take all the aluminum, use an electric current, and get a lot of it. Then it was being used, but not really used that much. In the 1920s, the killer application, the killer reason why everybody wanted aluminum, is we started using it in airplanes after World War I. All right? So you need that killer app to get adaptation. The material science is the study of solid matter. It investigates the relationship between atomic or molecular structures of a material and its microscopic properties. Examine and understand what influences these properties so that you get the right material that can be selected for a particular application. Folks, this gives you the tools. This gives you something in your, I should say, toolbox to help you design new things. If you were born in 1903, your airplane would have looked a lot like the Wright brothers because they simply didn't have jet engines then. They weren't even thinking of using aluminum. They couldn't make the motors powerful enough because they didn't have the tooling and they didn't have the materials to make the motors, the engines, strong enough. So we as engineers are limited sometimes. But this also makes a great opportunity for you chemical engineers or chemists where you come up with a new material. Wow, now we can start using it for all kinds of things. So it falls in ceramics, metals, polymers. All right? Now, what is a ceramic? It's inorganic, non-metallic structure created through heating and cooling. It's a crystalline structure. All right? Ceramics are generally brittle, hard, and strong in compression, but not other types of loading. In other words, they don't do real well with tension. A pull. They are generally better withstanding corrosive environments and high temperatures. You probably have Corning wire at your house somewhere. You can stick that in the stove and have nothing to worry about it. Metals, on the other hand, are good for electrical and thermal conductivity. The electrons can be easily removed. They're malleable. In other words, you can bend them. They're ductile. They can be stretched. And they have higher densities than non-metals. And these are iron, copper, gold. They've been around forever. Silver and tin. If we mix carbon in with iron, we get steel. You get nitinol. Is another one. Is a newer thing. It's a little bit of that memory wire kind. I believe nitinol is the memory wire stuff. One of those. What is a polymer? It's anything with repeating subunits. We see that a lot with the plastics. And, you know, not surprisingly, polyvinyl chloride, PVC, what we use in plastic pipe, is everywhere. Surprisingly, wool is considered a polymer. And shellac, rubber, nylon, all polymers. And so what we can do is we combine properties of each to come up with a composite, which is really powerful. So you have cement with water, with fine aggregate sand, coarse aggregate, gravel, and you get concrete. So it's, you know, sand and water, and aggregate sand. You get the special Portland cement, water, fine sand, gravel. You end up with concrete. So concrete is a composite. Wood, if you think about it, it's cellulose fiber. That's the cells and a natural glue called lignin, Lignin. And then tires, you know, that's made of rubber, but there's other materials in the tire. Think about it. It's got to be able to hold the air inside while you put big compressive loads on it, all right, as you're driving it. Now we're going to talk about glass. It's not a crystalline structure, so it's not a ceramic necessarily. And we're going to watch two videos that were put out by Dow Corning. Now, these are kind of a little infomercial about Dow, but they're really well done. It's done by two guys from Mythbusters. It gives you a sense of what new materials allow us to do. So here's the link. I'm going to go ahead and copy it. I'm going to share this with you all. So if you can't see it, this send to all. That way, if you want to watch this webinar, if there's too much delay on your program, on your computer because of internet connection, just go on yourself. So I'm going to go on Age of Glass right now. We'll go ahead and start that.
Pop quiz. If you were able to look back on the present from deep in the future, what age would you say we're living in?
Is this a trick question? I mean, I want to say information age, but
So we saw that in glass materials, and I just wanted you to see that once an engineer or scientist maybe comes up with an invention, figures out, wow, this is what graphene is, or this is how I can do something to glass. Then we hand it to the engineers who then implement it into our lifestyle. So she may be an engineer and she figures out a better piece of equipment. She uses that glass in an all new way for measuring things. Well, that aids the scientist who then goes out and uses these new tools to make some new discoveries. Think electron microscope, think MRI, think of those things. It becomes this circle, and that's how we learn. It's back and forth. All right? Now, I got a real quick, I want to do a real quick poll here, and then we're going to do some other things. Hang on. What'd you think of tonight's webinar? Come on, we need a couple more people to vote, and then we'll be all set. Or one more person. All right, we got 80. 5, 4, 3, 2, 1. Close the poll. Share results. A lot of people found it real interesting, which is awesome. Some people found it helpful. Great. I'm glad you enjoyed it. It's normally we don't show a lot of videos and things, but for this, they did a much better job than I could. All right, now, what I want you to do for the last 6 or 7 minutes here is I want you to finish your checker. So you need to finish your checker if that's what you want printed. Because if you look over here, hopefully it's, well, there it is. See the checker right there? That's what's going to print. Let me see if I can get it to go. I got to hook my printer back up on a cable network. But let me So you're going to get a chance to hook it up. You're going to be able to watch yours print. All right? So what I need you to do is it needs to be 45 by 45 millimeters, 10 meters tall, no more than that. Or you can print something bigger, but you're just not going to duplicate it. Oh, let me hide it. Sorry, guys. Let me hide it. Hide results. Okay. There it goes. Okay, sorry, I always do that. Now, make sure you save it. This would be, in your case, Iowa, Tom, Middle School, MS. Make it public, share the link on Edmodo, and then I can work on that. If you've already done that in Checker, you want to work on Code Combat, go ahead and do that. Okay? I'll stay on if there's a question or something. Otherwise, go ahead and work on that for a few minutes. I know I guess in just about 5 minutes you'll be having to go on and do other things, but here it is. If you've got everything done, you've got done with your checker, and you want to go, you can. But that's what I wanted to cover. I wanted to show you that you can watch your checkers print online now. We'll have that going on.